Hello class. So in Zoom today we are going to talk about this example problem, but in case you're having trouble with Zoom or if it doesn't load fast enough, I wanted to just give a quick recap. It's going to be low technology. I'll just draw out what happens in MATLAB myself, but this is just a way to quickly get the information so you don't have to watch Zoom. So we talked about how there was that using root locus we can design around any parameters as long as if we put in our characteristic equation as 1 plus k go of s is equal to 0, where go is what we can plug into our MATLAB root locus, and then we can visualize any effects of changing k. So the root locus will allow us to see where are the pole locations if we change k. I realize you're not taking notes on this, it's an example problem, so I'm probably going to speed through most of any long writing. So I wanted to do a little bit of an example to show us root locus for parameter design, or root locus for parameters. And there I go, not pausing. Well, we're doing root locus for parameters, and I want us to consider the example problem from homework 7, I believe it was, where we had a system represented with a characteristic equation s squared minus mu plus 2 s plus 2 mu plus 5 is equal to 0. And from the homework we had that this system was neutrally stable at -2 and -2.5. So we want to visualize the effects of changing mu, where root locus will allow us to see the locations of our poles as we change k. And one thing important to note is it will only allow us to see as we change k from 0 to infinity. In this case, the interesting parts of mu occurred when mu was a negative number. So we're going to let k be equal to negative mu. And we want to find our representative go of s, given that we want to track what's going on. So we can say that this would be s squared plus k minus 2, because we're going to have a minus 2 there, times s minus 2k plus 5 is equal to 0. And we want to get that into a 1 plus k times our go of s is equal to 0 format. So we can look at what's multiplied by k. So we have s times k in the first right here, and then we also have minus 2 times k. So those can be in our numerator. Everything that's not multiplied by k will be in our denominator. So that will be our s squared minus 2s plus 5. And this equation is equal to 0. So in MATLAB, we can plug in root locus of, and our numerator is going to be 1 minus 2. And I think we'd have to do root locus transfer function. So let's get some room for that. Transfer function, root locus, with a numerator of 1 minus 2 and a denominator of 1, -2, and 5. And that should be a 1 with a space for our -2 because, so we're just going to make sure that we are not doing 1 minus 2, but we are doing a 1 and a -2 with a space in between. And if we plot this, we can now visualize the effect of showing what's going on if we want to change k from 0 to infinity, which would be the equivalent of changing mu from 0 to -infinity. So if we place this go of s into MATLAB, and we're going to see that our open loop system has a 0 at +2 and complex conjugate poles in the right-hand plane. So it starts out as an unstable system when mu is equal to 0. Then, as we increase our k value or decrease our mu value, and let's go ahead and use a different color, we're going to have it become an underdamped second order system, and then move towards being a overdamped second order system. And so this one will match the other and then head out this way. And if we use our scope tool, which we don't have here, but for the sake of explanation, we're going to say that we can look at these values. So if we use a scope tool, it will tell us that our gain is equal to 2 at this point or at this point. And our gain will be equal to 2.5 at when our pole crosses back into the unstable location. So that matches with our expectations, where it tells us that when k is equal to 2 and when k is equal to 2.5, that's the same as saying that mu is equal to negative 2, mu is equal to negative 2.5, that's when our system is neutrally stable. And when we're between those values, we have a stable system. But once we get to the point where we cross back over into the right-hand plane, the system is no longer stable. So that's how we can look at the effects of changing a parameter on the location of our poles. So this was using an example from the homework.